Hi everyone, this talk will concern learning model parameters from dynamics, from watching models evolve with an unknown observation function. My name is Amir. This is work done with my colleagues Ophir, Gal, and Ronen. We have just put it on archive earlier in September, and to be honest, I am quite excited to be giving a talk to a large audience about this project. Before I go on to tell you exactly what kind of problem are we solving and how are we solving it, I will tell you about an experiment. Experiment simple enough that you've probably done it in your undergraduate studies, if you studied physics. Well, you're given a pendulum. A pendulum is a string, one end is nailed to the wall, and a bob, a weight, a ball at the end of it. And you are asked to use this apparatus to measure the gravitational free acceleration g. So g is a known number, but this is an undergraduate experiment, so you are trying to estimate it by yourself. Well, here's how I would do it, and probably how you were instructed to do it too. So we know the ODE, the ordinary differential equation, that governs theta, the angle of the string. So we know that when we solve this ODE, this harmonic oscillator ODE, we get periodic oscillations, cosine and sines, basically. And we know that their frequency looks like G over L, L being the length of the string. We can measure L with a measuring tape. And if you have a clock, you can watch how many times does this periodic motion crosses through the origin, through theta equals 0. And you extract G out of that. A simple enough way, a very elegant way, to watch a dynamical system. And from comparing it to the known model, known parametric model, I should say, extract G, the parameter of interest, the unknown parameter. Now suppose someone have some chutzpah, or someone gets confused, and he wants to do the same experiment now with the double pendulum. Maybe he thinks that a double pendulum is better than a single pendulum, right? Always supersize me. Okay, so now there is a string, a bob, another string, another bob. And while this is a much harder system, and writing the ODEs requires some Lagrangian and some interesting things, eventually you do get a system of ODEs. And again, while we cannot solve the system of ODEs by hand, we can certainly code it and solve it on a computer for every set of parameter. So what are the parameters? Will be G, L1, M1, L2, M2. Okay. Now you want to say, I will observe the double pendulum chaotic trajectory. Oh, now it's chaotic, by the way, yes. But I will observe it and I will compare it to the model and I'll be able to extract all sorts of things. So now I said that pendulum is chaotic, it's not periodic, so there's no simple parameter like omega to extract. And also, if you just see a frame, so this is an experiment that I found on YouTube, and you see that it's really hard to see. It's really hard to see the two. Here it's not bobs. Here it is two metal plates, but still the same principle. And you see that there's this smear, and you don't see quite well. And we tried actually to manually zoom in and measure the angles. It's really hard. It's not so obvious. So there's a lot of problems with implementing the single pendulum approach on the double pendulum. It's not obvious how to make the correspondence between those clean theta that I write down in this drawing to what you actually, the raw video, what you actually see. And it is not obvious that there is an easy observable, easy meaning a number probably, that we can observe, extract, and then extract from it G. Schematically, the problem is as following. There is a parameter So I wrote here all of the parameters. It might be just a subset of them. And we don't know the real parameters, okay? So underlying the system we want, you know, it's a model that we know. It's a meta model, let's call it, a known ODE that generates for every parameter set coordinates, this x vector. So in this example, it's a fourth order ODE, so it makes sense to think about it as x as something in R4, or you can think about the coordinates in time, so x, y for each bob. It's low dimensional, and for every omega, we know how to generate the coordinates. The only reason we don't know the true coordinates is because the real parameters are unknown to us. But then there's another level of complication. Instead of observing x, we observe y. Y is extremely high dimensional, so in this example, it's in R million, just a million pixel in a picture. And the relationship between x and y is some unknown observation function. So there is a function g, which takes x's to y's, takes a coordinate, a point in phase space, to a movie frame, but we don't know it. And generally, this problem is, and I'm starting to introduce the notation that we'll need. So you have omega star. This is a true underlying parameter that we do not know. And known ODE pushes it forward to a model. So a model is the coordinates with some parameter. And then there's an unknown observation function g, and the only difference that I'm introducing here is the randomness. So think about randomness as an all-encompassing term for every kind of problem that you can have with g that doesn't make it quite deterministic. So there might be noise, there might be some uncertainty, there might be inherent stochasticity in the observation, and all of those things I just encapsulate in zeta, the random variable. So let's see what is unique to this problem. So first of all, there is a single experiment. There is a single omega star, and the system we observe has a single movie y of t. Now think about, why do we make this assumption? So think about the double pendulum. If you want to extract little g, for example, there's probably only a single little g as long as this experiment is done on Earth. Certainly, other problems might have the luxury of having multiple movies of multiple omega star, but in this talk today, there's going to be a single omega star and a single movie. The benefit is that this is a dynamic experiment, so the movie y of t is made of a lot of frames, consecutive frames. And finally, the big problem, the big twist, if you like, of this problem is that we don't know g. So you know what you're observing. You know that you're observing a fluid, a laser beam, the growth of a tumor, the response of the subsurface to acoustic shocks, but you don't know exactly how. You don't have the exact correspondence between the model that you are observing, between whatever models what you observe, between the actual observation. It is interesting, certainly in this workshop, to compare it with two extremes of this world of machine learning and data techniques with physics. So one extreme is inverse problems. Now there are a lot of inverse problems, so obviously I will say something quite general, and different variants have different differences from this generality. But still, in a standard inverse problem, I would have an unknown parameter omega star, and there's a full forward map. So in our case, it will be x and g, and this forward map is known to us. And the question is, can you do quote unquote g inverse of y? Now, of course, this is only the starting point, and there could be a lot of complications. So usually, it is impossible or ill-posed to invert g. G might be too noisy to invert. There might be some prior knowledge on the parameters. So you would like to find some parameters more than others. But all of these problems will have a known forward map. And certainly in our case, the forward map is not known. It is only half known. We know the map from omega to x, but we do not know the map from x to y. The other extreme end, that there will be a couple of what seem to be very promising and interesting talks, is model discovery. Again, there are a lot of model discovery problems, but if I had to generalize, I would say that you are given many observations, x, you observe x, you know what you observe, and you really want to find the ODE. So when I say find the ODE, you either find it explicitly or implicitly. And you might not observe x, you might observe some lift, some observation function in our language of x. And the observation might be noisy or partial. But in all those cases, there is a learning aspect. So you see many, many examples, and you see what you want to model. And again, in our problem, you see one movie, and you don't see what you want to model. Okay, so that's a big difference. So we sit somewhere in between model discovery and inverse problem, and I'll say it now, and I'll probably say it in the talk as well. I do think this is a new way to think of problems. So I think mathematically, this is the first formulation, at least the first I know, and I'll be interested if any of the listener or viewers know of relevant papers, the first formulation of this sort. And so I think it is also interesting, before I go to the solution, I think the problem is in itself interesting and new. So what will I say today? I will tell you a couple of naive solutions, really a procession of naive solutions. Each of them will not work or will not be even computable, but it would lead us to another naive solution and then another naive solution, until finally I will tell you about the kernel approach. After I'll tell you about the kernel approach and I'll describe the algorithm, it is fairly simple. I'll show you two results, one for the double pendulum system and another for the Lorentz 63 system. So let's go. So I'll keep, if you see above, shadowed is the system, is the schematic. So if you get to forget one of those parameters, notation, who's omega, who's f, it's always above here. So certainly when you're watching the video, you can pause and look at the scheme above. So now I said naive, so let's be fully naive. Suppose we know G. Okay, if we know G, we're in an inverse problem setting. And there are a lot of ways, depends on a lot of factors. But I will just highlight one very, very naive way that oftentimes work, not always. And it will be more than a statement about how to solve inverse problem, which I'm definitely not going to make today. It will lead us towards the solution that we'll actually adopt eventually. So if you had G, you can do the following spiel. You can say, let me hypothesize that a certain omega is the right omega. I will plug it into X. I will plug X into G. Remember, I know G. And now I'm not comparing oranges to apples, X's to Y's. I'm comparing apples to apples, Y's to Y's. Good, I'm comparing them. So I'm comparing the L2 norm in space, L1 in time, and I want to minimize it. Of course, if I had omega star, this would be 0, so I want to minimize it. And we know that this might have some issues, but generally speaking, this is a robust way. And if G is well posed, if there is a solution, and if there's a unique solution, then this estimator should be reasonable. And again, the theory of inverse problem makes this sentence rigorous for some problems. I want to imitate the scheme without knowing G. When I say imitate the scheme, let me introduce a couple of more notations because we didn't have enough of them. So I have a capital Y matrix with the columns just Y at concrete times. So that's the data matrix. And then for every hypothesized parameter omega, I can produce the model matrix, X omega. So different samples and different coordinates. And as a generalization, as an abstraction of the least squares approach that I just showed you a slide ago, I want to have some score that takes, again, model matrix and data matrix, apples and oranges, and compute a score. And I want to maximize it or minimize it, depending on the score. And that maximizer will be omega hat, will be my estimator for omega star. And now, of course, the key question, I haven't told anything if I haven't told you what is that score. But at least this is the approach. This is the schematic of how we'll solve the problem. And now let me say, we do not try to reconstruct G, right? So one way to solve the naive approach that I showed you a slide before would be to reconstruct G. We do not deem it feasible to reconstruct G because, again, we only have one movie. Okay, so I will not assume that I know G, but I will assume that the unknown G is actually a matrix A, and I'll assume that the noise is normal in IID. So something that looks like this equation. I know there are a lot of ways to solve it, but allow me to go ahead with one of them, and that's the maximum likelihood approach. I want to seek omega hat NA, which make the data most likely. If you work out the math from here to here with the above assumptions, you will get this formula. Now, I'll tell you, I will read this formula, but really it's important to say that between here and here, I didn't make any further assumptions. I just computed. Okay, so what am I reading here? The important part is that I'm using the Frobenius inner product, the trace of B transpose A. Now, if we had continuous signals and not discrete in time signals, this would be an integral over time of the L2 inner product, but it's easier to work with discrete, so we will be working with the discrete settings from the get-go rather than discretizing the end. Both approaches could have worked. So there's an inner product, it looks like correlation maybe, and it's normalized by the own Frobenius norms of the matrices. And I want to say this is computable because A is a matrix, so it has, so for example, for the double pendulum, this will be 4 millionths parameter. So in principle, this is computable. Of course, you can argue and you'll be perfectly right that this is not tractable. Well, but at least it's computable. Okay. So that is what we'll get if A is linear. Now, you can say if G lives in some finite dimensional space, you can still run the same spiel without, instead of a matrix, you can find the G that maximizes this thing. Now, I'm not writing, from now on, I will not write that I'm looking for G, just argmax, but certainly I'm looking over all G and over all omega. Entertain this for a moment. Of course, this is not what we do, because generally we can say that G lives in some finite dimensional space. But even though G is unknown, then at least we know that there is a G, right? So we know that if we take G here and the identity here, then there are two maps. Let's call them phi and psi. And again, this will play in a kernel method session. So for those kernel methods people, these are the feature maps, close parentheses. And if we were lucky, then the noise is additive after the maps are applied, and then you get this expression. So again, from 1 to 3, these are just names, naming names and defining definitions. We know they exist, and so we can write it. And I'll just say that the linear additive noise is restrictive. It helps the analysis. From judging from the numerics, it doesn't seem necessary. Okay, so now we have to start doing things because we know that phi and psi are unknown to us, and we know that they generally live in an infinite dimensional function space. All right. So what we'll do, as one often does in kernel methods, we'll first observe that those inner products, the psi in different times and phi in different times, yield kernels symmetric matrices kx and k super y, And we further note that the denominator here can be written in terms of those kernels gram matrices, where H is simply the centering matrix. So the kernel trick will be as follows. It will say, instead of seeking find psi, assume what the kernel is, and you will choose a kernel based on your intuitions and heuristics about how samples are similar to one another, how time I and time j relate either in x or in phi. And if the kernel is expressive enough, it reconstructs or partly reconstructs the inner product of the real feature maps. So I've written this down, but now note the kernels are kernels that we chose. So let's choose the Gaussian kernel. Okay, so we already moved a step forward with the denominator, but we're still kind of stuck with the numerator. So what you notice, if you do the math, you will notice that the numerator is the cross covariance between psi and phi squared. Okay. We don't know, as of today, as of the writing of this paper, how to express this guy in terms of the kernels. But we do know how to express the trace of C transpose C in those terms. So we approximate now. If you're completely rigorous, and you ought to be, then you notice that now this expression is no longer this expression. So it's not exactly the maximum likelihood estimator, even if the kernels were exact. But we can proceed and write this. So now note that everything here depends only on the kernels and the known matrix H. For every omega, we can compute the kernel X. The kernel Y we compute once. And so this green formula is completely computable. I want to give you two different perspectives about it, because this expression doesn't come from thin air. So if you look only at the numerator, and I can't stress it enough, only on the numerator, then you see that the numerator is the Hilbert-Schmidt independence criteria. What is it? It's from the works of Gaussian and Tal. It's a way to express the dependence of x and y's as random variables. So you can think about it as nonlinear correlations, correlations under a vast family of nonlinear functions. Another way is to say, suppose x and y's live in a product space, xy, then if you want to estimate the probability that they live at a given point, then this is the kernel density estimator. So you can think about it as a sort of problem in non-parametric statistics. This is from a work on computer graphics, but by Wessner and Bronstein, and I think it's also a very interesting way to look at it. The key difference between their works and ours, in this sense, is that normalization for us is key. So I'll give you one example. In the work of Wessner and Bronstein, the different parameters are permutations, so the norms never change. This is not the case in our work, and we've seen it both in experiment and it makes sense in theory that one needs to normalize. So this is a judicious way to normalize the numerator, and you can also show that under standard conditions, this is the right, in some sense, normalization, and for this I'll refer you to the lemma in the paper. An algorithm, finally an algorithm. So even if you don't believe or care about the heuristics or just want to see an algorithm that solves the problem, here's an algorithm. I'm choosing a Gaussian kernel for k super y, and I compute once and for all the kernel y. I set a grid. It could be a Cartesian grid. It could be any set of hypothesis points in capital omega. And so for every small omega, I solve the ODE. I compute the model kernel, k super x, and I compute the score, the same score that you just saw. What do I return? I return as het omega, the estimator for the true parameters, the maximizer of the score. Now let's see that in practice. So here's the double pendulum. Here's the ODE. It's small enough so you don't even try to read, but you can certainly code it and run it on MATLAB or Python. Here's a frame of a synthetic video. And here, just to show you how long the movies were taking and how chaotic is trajectory, this is the trajectory of the lower bob where color is just time. So first of all, an anecdote. Here's a single run of algorithm 1 with certain parameters. It's not such a long run. It's not such an delicate run in terms of high resolution. Black lines show you the location of the bob for the true parameter, and the blue dotted lines, the locations of the bob of the estimated parameter. So x1, y1, x2, y2 as a function of time, and you see that the agreement is quite good. Sometimes it's not perfect, but most of the time it's quite good. Okay. Let me say something before I tell you about the estimation. Let's just pause here. This is a well-known thing for people working in inverse methods, but I think it's worth iterating. If the agreement is good in the trajectories, but not good in the parameter estimation, that means that there's some degeneracy in the problem. There's some identifiability problem here. So this is the best you can hope for, sort of. You can hope for less error, but if this goes well and the estimation doesn't go well, well, the problem is sort of ill-posed unless you enforce some more regularity or some more conditions or some priors. But luckily, this problem is quite well posed, and you get from the grid search estimation error of 5 to 8%. So those are box plots, red lines being medians, blue standard deviation, red are outliers. Okay. But not all is well. The grid has two main problems. First, it's not accurate. It's not as accurate as possible because your accuracy is limited by the grid spacing, basically. The efficiency is also not so great because you're doing a full grid search here in a three-dimensional space. So a three-dimensional space, the grid is scaling to the power 3. Think about the 10-dimensional space, that becomes hard. 100-dimensional space, you can forget about it. So the natural thing is to think about optimization. So the algorithm is really the same, only with two differences. For every initialization point, we run an optimization scheme. So that optimization sample in capital omega according to its own protocol. In this work specifically, we use interior point algorithm, but you can use other methods as well. And we run it several times. And we run it several times. I will say it now and I'll explain it in a minute. We run it several times because we know that the problem is not convex. And so we try to compensate for the non-convexity of this problem. Okay? And what do we return? For every optimization run, we return some omega pre-hat, and then omega hat is the maximum over all those iterations. And we observe that the results are quite good. The accuracy improves in a factor of 2 or 3, and the runtime improves by order of magnitudes. It's much faster. And even though the problem is not convex, we see convergence quite fast to quite accurate parameters. I have to say now why this problem is not convex. And I will explain it. It's not that it can't be convex, it's rather than more often than not, you would expect it to be non-convex. Suppose this is the parameterization of your problem. Then I can suggest you a different parameterization of the ODE. So instead of omega, there will be theta, instead of f, there will be g. So it's the same ODE. If this score, the score that corresponds to this ODE, to finding the best omega, is convex, we can reparameterize it to be non-convex. So now flip this on its head. Well, your original parameterization is most likely non-convex. And I think it's an interesting problem that one would like to study, and I personally would like to study. Can you take an ODE and reparameterize it so that this algorithm, algorithm 2 that I just presented, is a convex optimization problem? I think this is the right way to go. You take the ODE in the canonical, natural textbook form, and you reparameterize the parameters in hope of making it convex. Something to study, something we haven't done. Now I want to say another point about algorithm 1 and algorithm 2. You could have asked, and you would be right to ask, well, maybe this is an overcomplication. You told us that what you're really comparing are correlations, nonlinear correlations between different times. What about linear correlations? What about linear variants of the algorithms? And what you see here is that the natural linear variants, and again, I'm not spending too much time in presenting them, but they are there and you can watch them. You can see the actual formulas on the paper, yield much, much, much worse results with accuracy in the tens of percents instead of the single digits. So somehow the nonlinearity really kicks in this problem, and you cannot be satisfied with naive linear algorithms. Can you do it without kernels? Perhaps. Can you do it with a naive linear approach? It seems unlikely. Okay, another example. So this is a Lorentz 63, and it's a well-known ODE. Here it is, it's a three-dimensional ODE with three parameters, sigma, rho, and beta. And we have borrowed from the Bronton-Proctor-Kutz paper this nonlinear map that has to do with the Legendre polynomials. It's nonlinear, it's from 3 dimensions to 128 dimensions. And again, we know it, but then when we run the algorithm, we pretend as if we don't know it. Okay. And now I want to say that we add the noise to the model and then apply the nonlinear map. So now we can say that the noise is not white additive Gaussian noise, but some convoluted thing that has to do with the nonlinearities here. And again, if you remember the beginning of my talk, I told you that I want to show you that, at least from a numeric, from demonstration point of view, additivity is not necessary. It doesn't seem to be necessary. So again, we begin with an anecdote. So you see that the black lines or the dark blue lines are the real thing. The gray lines are their noisy version. The dotted lines are what we estimated based on the non-noisy version, and the red lines is what we estimated based on the noisy version. Now, certainly there are some errors, mostly in the red lines because it is based on a noisy version, but you see again that the agreement is quite good. And the results are good. You get single digit, slightly below and above the 10% error, both in the optimization method and the grid search method. And what you can see more is the oracle. So now, why do we present the oracle? Who's the oracle? And what does it tell us? So you might look, for example, at the grid search and say, well, gee, this is 12, 13% error median. This is not so good. So maybe the algorithm is not so good. Even if you go to the optimization, you see that you get for sigma around the 10% error. And why is the error in sigma so much larger than the error in rho? Maybe you're not looking intelligently enough. The oracle says the following. We run algorithm 2, the optimization, but for a known G. So we're really running the first naive problem of least squares for a known G, and we try to optimize on that. And you see that you don't get such good results. And the reason you don't get such good results is because the problem is ill-posed. There are a lot of degeneracies. There is a real identifiability issue here. And so when you look at that, when you look at the optimization and the grid search and you compare them to the Oracle, well, it's not so bad. It's pretty much what you would expect, and it's pretty much the best that you can get. Best you can get without imposing more conditions. So this is always something that you want to look at when you try to judge whether the results are good or not. This is it. This is the paper. There are more things written in it than I presented, but I wanted to keep somehow the movie short. And I look forward to see you in the live sessions. Thank you.